Okay, and here we are for the inaugural session of teaching human factors online. I am, of course, your famous professor, Harry Whiting, and I hope that all of you are bearing up well under our current COVID-19 situation. I know I'm going a little bit crazy because of not being able to get out and do what I want, but I hope all of you are social distancing and otherwise taking measures to make sure that you are keeping yourself and your family safe. All right, so that being said, let's plunge boldly back into Chapter 6, Cognition. We had left off on measuring situation awareness. Situation awareness is realized to be important by its presumed absence after an accident. Boy, that's some good spelling there. All right, there we go. And realized, and Bob's your uncle. In other words, we're often thinking about situation awareness and how important it is after something has happened, and often it's being imputed that that was the cause of an accident, or at least a contributing factor in an accident afterward. However, measuring by presumed absence after the accident, where we're presuming situation awareness equals 0, is not the same as understanding situation awareness in a system beforehand. So one way that situation awareness is measured is by asking questions about the task during the operation of a system. Now, this obviously is kind of a weak way of measuring it, because we don't know for sure if the situation awareness is interrupted by this method. Self-evaluation of situation awareness is used and scaled from 1 to 10, but we're this is a weak way of measuring it. What can you do? All right, so we have we want situation awareness, obviously, to be part of a system. Whether we're talking about just walking across a factory floor, or we're talking about or we're talking about someone who is actually running a system, monitoring the system with dials or displays. So our situation awareness is important in human factors. One thing is designing easy to interpret displays. All right, because we want to help people notice what's going on. Right? Obviously, that is stage one, as we discussed above, perception. We want them to interpret and understand the meaning, right? Stage two, understanding, and we want them to predict future implications. Okay. Right, which of course is our stage three, prediction. Now, a potential difficulty is with what we called lagged or sorry, the cat wanted to help out by brushing up against the camera here. Lagged or slow okay, she wanted to help so much she knocked the camera off. All right. Hopefully that will be it for Katniss for a while. Lagged or slow response. If we're talking about a system where if we're talking about a system where it takes a while for changes to register in the system, then there may be a problem with prediction and with running the system. An example would be the Dow Chemical accident in Bhopal, India. In Bhopal, they were making a chemical, I believe it was an insecticide or a pesticide of some kind that was dangerous to humans in concentration. The system, they were making the chemical in a system, but in case the system started to get out of control, you could open a conduit to a larger area to temporarily slow down and give you a chance to react and stop the process. The problem was when they did that, all the readings went to something that they're saying, oh, now we're fine, everything is in great shape. But of course, all that meant was that there was a time delay before it built up again to a danger point. Then when that danger point came, they had no way to react, and the chemical vented and thousands of people died, and oh, how exciting that was. So we can have a problem when we have a slow response in a chemical reaction situation like that, in a situation where it takes a while for control of any kind to respond. Super tankers are a good illustration of that. Super tankers now are so large that they don't start responding until considerably after input is given to them. So it can be a thing of you are turning the wheel to turn the ship, but it does not begin to even respond for minutes after you've done that input, because a supertanker is so huge that its weight and the amount of the tanker in the water slows the response way down. All right. So that gives us a problem. Oh, God damn it! Luckily, my cat knocked over my. There we go. The book. So I lost my place there for a second. All of the things I talk about in this video and in my ordinary classes are straight out of the book. The last time I did this class, I meant to then take that outline and make slides to make it easier to go through, as I have been criticized for not doing. But somebody erased my outline last time before I could copy it, and so now I'm having to start again in this class. All right, but okay, so one thing about it is design to enhance performance may not support our situation awareness. Okay, so as usual, taught 2, there we go. As usual, our goals may be contradictory in human factors, and we have to weigh which of those that we're going to think about. Our situation awareness can be important in accident analysis. One of the things that we worry about, of course, is accident analysis. What happened in the accident, and what can we do to prevent it in the future? One thing that we always need to remember is that usually an accident is a chain of events that lead up to a problem. It's not just that one thing happens and then you have an accident. All right. And we need to think that situation awareness has implications for training. Training for routine performance may conflict with training for situation awareness. So that's certainly okay. Well, be like that then. So that's something to keep in mind. One of the complaints that astronauts had about the early training in the American space program was, they said, it seems like all we're doing is training for things to go wrong. So they had gone totally the other way, in that they weren't training for routine performance as much as they were training for the accidental situations. All right, so let's move on to problem solving and troubleshooting. All right, so problem solving and troubleshooting are often very closely linked. They have overlapping elements within them. All right, so there is a difference between the starting state and desired state. Or they call it in the book a goal state. Typically, this requires a number of cognitive operations to reach the goal. That's not how you spell troubleshooting. All right, there you go. So troubleshooting is embedded within problem solving. We have to understand the problem before solving. Okay, oh, that's not what I wanted. And there we go. So sometimes we're solving by trial and error just because we don't have a good enough understanding of what the problem is until we solve it through serendipity. We accidentally stumble on the right solution. So problem solving and troubleshooting involve attaining a state of knowledge. Typically, they involve performance of specific actions. So troubleshooting involves a series of tests whose outcomes are used to diagnose the problem. Problem solving involves actions to implement the solution. both of them are iterative processes of perceptual, cognitive, and response-related activities. Interactive, no, it, all right, oh, there we go. Iterative, perceptual, there we go. Meow. Oh, sorry, talking to the cat there for a second. All right, so what are the challenges with troubleshooting and problem solving? Well, first of all, both of them impose a heavy cognitive activity. If you encounter a problem often enough, that won't be the case, right? If you happen to know immediately the correct response, that when your car won't start, if you thump the dashboard, it does something that makes it makes the contact work that wasn't working before. Then you have a kind of an automatic response to the problem. But a lot of problems aren't going to be so simple, and you're not going to have kind of a canned process. So, uh-oh, what happened? Oh, okay. All right, so in your working memory, you're going to maintain 2 or 3 hypotheses of the problem, right? And obviously, depending on what it is, there may be way more than 2 or 3 possibilities. I should say active hypotheses. So, let's say problems source. So, more than this overwhelms the limited capacity of working memory. Okay, more than this, not less. So we're usually working with a very limited number of hypotheses when we go to solve the problem. So therefore, troubleshooting is subject to well, damn it, I've lost my place. So we're working with one hypothesis at a time. So our troubleshooting success depends on attending closely to the cues and test outcomes. And of course, if a test outcome disagrees with your hypothesis, you may not be paying much attention at all. All right, got to be more careful about watching where the text is compared to the shooting here. Right, so you have attentional biases and perceptual biases coming in as part of the troubleshooting right? So that means that we may have, actually I should have left it over there. All right, so you may have very salient outcomes, right? Bottom-up processing, or you may have anticipated outcomes, right? And obviously that's top-down processing. All right, one thing that happens though is people don't notice absence of something. So for example, it might be that a certain warning light is not on that would indicate some kind of a problem, but we don't necessarily notice that and take that in. Right, we also have the what we call cognitive tunneling, or confirmation bias. In other words, we have already made the decision of that a certain hypothesis is the one, right, where we may be looking for cues to confirm, right, in a top-down processing way. And interpret ambiguous data to confirm our biased hypotheses. So we may be applying solutions that aren't working as a result. These are likely to manifest when, first of all, we have high system complexity. Right? In other words, how much are there different competing aspects of the system that might be problematic? A lot of different things are coupled together in various ways. And part of that is that complex systems are more likely to produce incorrect models of the system. Oh, pardon me. Oh, well, maybe y'all didn't hear me there. All right, so and okay. So intermittent failures of a system component are particularly difficult to troubleshoot. Okay, well, oh, damn it. All right, here we go. All right, so so we have the troubleshooting and problem solving. Often, again, they're linked together, particularly when we're trying to find a problem in a system. Now, that's not to say that problem solving, when you're, I don't know, doing some math homework or something like that, is necessarily in the same category. Although my tendency is when I do math to go back and troubleshoot and check my answers. All right, well, there you go. All right, so let's move on to planning and scheduling. These are closely related to problem solving and troubleshooting. Because, of course, we're going to be looking at it and we're going to say, all right, if this test fails, that means that I go to this other thing I'm going to do, or something like that. However, problem solving and bloody hell, troubleshooting imply something is wrong. Where planning and scheduling do not. All right, so in many dynamic systems, we have two components. One is the predicted state, and the ideal or command state. So when we have that, sometimes, as we talked about before, or I talked about it, maybe you're talking to yourself about it. We may have sluggish systems. In other words, that the kind of lagged system that I was speaking about before. So in a sluggish system, we have to have longer range planning. We have to think longer term because it's important that future production matches future demand. Demand, is that the yes. Although demand has two D's. It comes back to me now. So sudden changes in demand in these sluggish systems cannot be met with sudden changes. Right, so we have to think very carefully about that. There are always going to be plenty of processes where you won't be able to just suddenly change the system to react to a sudden change in demand. Okay, well, I think I've beaten that idea to death. All right, so when we think about situation awareness stage 3 in that's expressing an accurate estimate of the future state and future demands. So our skilled operators may be running a mental simulation to infer the future state. We need to note that there are heavy demands on working memory to run an accurate mental model. Right, so that implies heavy demands on the cognitive resources. Oh, worst spelling of resources ever. All right. All right. So people tend to avoid complex optimizing planning schedules over long time horizons. This goes back to something that we talked about before. In general, people don't predict the future well. And it brings up problems. For example, part of this is a desire to conserve the resources demanded by working memory. Also, people have learned the lesson that in an uncertain world, accurate planning is impossible. Plans need to be revised or abandoned when things don't turn out as predicted. All right, so so we have this problem that when we predict the future, it goes back to something one of my professors used to say. When we predict, we will be wrong. We can absolutely guarantee that. So what do we need to do? What we need to do is constantly be revising plans. I'm struck by something that Eisenhower used to say, which is when we plan, what he said was planning, the plan is nothing, but planning is everything. In other words, we need to keep making plans because that helps us with our prediction of the future, but we should be able to abandon those plans at any time, because otherwise you get a situation called plan continuation error, which is obviously we're continuing to do the plan even as it becomes obvious that the plan is outdated or not effective. All right. Well, So let's go back to a higher, there we go. So what do we do about this? Well, often we will create predictive displays. Right? So that's going to be a visual representation of the likely future. Right? That may be against the actual situation that we have now, or it may be on its own. Right, this can be a computer-based planning aid. Right, which can either recommend plans or allow fast time simulation. Oops. Right. So all right. So planning and scheduling generally are hard. Now, of course, as engineers, we kind of expect you to be able to do that. So there you go. Bob's your uncle. So let's move on to the next section, which is metacognition and effort. So our performance is linked to a to our perceptual information and long-term memory. Right, and obviously that's about the task we're doing. All right, so one of the things that we talk about in this regard is knowledge in the world and knowledge in the head. We often refer to this as meta-knowledge or metacognition. scroll up here. All right. This refers to people's knowledge about their own knowledge. Of course, we've all seen the situation where we have somebody who is so confident, even overconfident in their own knowledge, that they end up tripping over their own situation. All right, so one aspect is the anticipated effort required to gain knowledge. A lot of times we will blunder along without seeking more knowledge because we will be worried about how much effort is required to get that extra knowledge. So we're asking ourselves, will the gain in knowledge be worth the extra effort? So this is a metacognitive trade-off, because knowledge in the world, the type that you have to gain by effort, is more accurate but more effortful. Whereas knowledge in the head is easier, but potentially less accurate. But when we design, we should realize that people tend to be overconfident about their own knowledge. Okay, so remember that till you die, as one of my professors used to say. All right, so we've talked about attention before, and attention, of course, is acquiring knowledge from the environment. So that selective attention requires effort. So when we when we're using that kind of selective attention, God damn it, it does require effort. Now, of course, human beings like to divide attention between two or more tasks. Oh no, that's not what I wanted. There you go. Right, that can be between two or more tasks or mental activities. All right, so four factors contribute to success or failure of divided attention. All right, so there's resource demand, and we're going to go into these some more in a few minutes. So there's resource demand, there is structure, there is similarity, and resource allocation or task management. All right. So, mental effort and resource demand people in general are effort conserving. They tend to avoid high effort activities. Or do them poorly. All right, let's fix activities. All right, so we try to conserve our effort. As a result, we tend to avoid our high effort activities, or we may do them poorly. So, high mental effort degrades the ability to do a second task at the same time. So you can drive and talk at the same time as long as one or the other, or as long as both are pretty easy. If you have to do a high effort task, you're driving a very difficult and winding road, or you're having to discuss something very in-depth and complex, you may have a problem handling the two tasks at once. Resource theory talks about the relationship between single task difficulty and dual task divided attention. Deficits. Is that how you spell deficits? Doesn't matter. They use decrements. In the book. All right. So our scarce mental resources shared by the tasks, so more difficult tasks leave fewer resources for concurrent tasks. This is something that human factors experts have been talking about for a while, that that when people talk about multitasking, really what you have is serial processing. That, in other words, you spend a few fractions of a second thinking about one thing, then you spend a few fractions of a second thinking about another thing, and so on down the line. So obviously in that scenario, it is not as easy to have everything going smoothly when you're doing multitasks. All right. Well, automaticity means that the task is automated so an example would be signing your name, or logging in, logging in to a familiar computer. Okay, I'm coming. All right, so it's highly practiced. It's there you go, practiced. So it's highly practiced, carried out rapidly with little thought, and demands few mental resources. And automaticity is a thing of degree. In other words, some things are very automatic. Some things you have to think about a little bit more on down the line. All right. Well, I am going to end this lecture here. I still have to upload it to to Moodle for y'all to be able to see it. And that's probably going to involve having to convert the type of video it is so that y'all can read it. So anyway, have fun. I'll have the next lecture linked in soon. And I'm trying to figure out homework that is appropriate for our current situation. So thank you so much. Again, I'll see you again whenever spring breaks through again, as the poet once reminded us.